Hello there, Advanced Chemistry, and welcome to Notes on 5.1, Part 2. So we had already talked about how to assign oxidation numbers to atoms in a compound or polyatomic ion. Today we're going to talk a little bit more about identifying a redox reaction. And so in order to determine if a chemical reaction is redox, you have to see if any of the atoms' oxidation numbers change. So we identify what's called a reducing agent, which is the atom or atoms that are oxidized, and the oxidizing agent, which is the atom reduced. So in other words, what you have here is the atom that is oxidized is the reducing agent because it is supplying the electrons for the atom that is reduced. And the oxidizing agent is taking the electrons that are supplied by the reducing agent. So they're opposite. The reducing agent is actually what's oxidized. It's called the reducing agent because as it is oxidized, as it loses those electrons, it gives them to the thing that's reduced. So that's a little bit confusing, but the agent of reduction is what's actually being oxidized. So it facilitates reduction. Remember, this is all just, we talked about this yesterday, you cannot have one of these without the other. If something is reduced, that means something else had to be oxidized in order to get there. So what we want to do here is look at some redox reactions. Certain types of reactions are always more likely to be redox. We're going to do some examples. So synthesis would be an example of that. Decomposition is usually redox. Single replacement is usually redox, and combustion. So those four, and then double replacement's usually not. So again, there's always exceptions to these, but basically speaking, and I put a star next to single replacement because that's always redox, always going to be redox. Just a rule of thumb. So pretty much everything can be. Single replacements are usually 100% of the time, and then double replacements not usually. So that's just guidelines, and we'll do some examples. So we have a synthesis-combustion reaction both at the same time in which hydrogen gas and oxygen gas are going to create water. So what I will just do is write the formula equation here. We have H2 plus O2, and states are really not important for this, and then H2O. So we can identify this as a redox reaction by looking at the oxidation numbers for every species and seeing which ones change. So H2 and O2, the H is going to be really easy as it is an uncombined element, so it's going to be 0. And oxygen, same thing. And then over here in the water compound, start with oxygen. Since it's not a peroxide or bonded to fluorine, it's going to be -2. And hydrogen also is normal, so each hydrogen is going to be +1. So right away, what we can see here is that the hydrogen goes from 0 to +1. And so H2 is oxidized, and its oxidation number goes from 0 to +1. And as you can see, O here, I'll use a different color. O goes from 0 to -2. And you always write the whole species. So H2 is oxidized, so each H is oxidized. Each H in H2, and each O in O2 is reduced. Because it goes from 0, and it's almost like it's gaining 2 electrons, is reduced. So its oxidation number is actually reduced. Okay, so that would be an example of a redox because you can easily identify something that's oxidized, our hydrogen atoms, and our oxygen atoms are being reduced. Let's do another one. Decomposition. Here we have hydrogen peroxide decomposing into water and oxygen. So hydrogen peroxide is H2O2, and it's going to decompose into H2O and O2. And in order to balance this, I'm going to need a 2 here and a 2 here. Now, the coefficients aren't really super important right now, but they will be down the road, so just trying to be complete. So if I take a look at my oxidation numbers here. Here we have a peroxide actually. So oxygen in a peroxide, it says, is going to be -1. And then H is going to be a +1. It's not in a hydride. Over here in water, you have +1. And then you have a -2. We just did that one. And then this O is 0 because it's uncombined. So we actually have a really interesting thing going on here. Some of the oxygens in H2O2 are being reduced when they go from the O2, the peroxide, to the oxygen in water. And then some oxygens in the H2O2 are actually being oxidized as they go from -1 in the peroxide to 0 in the elemental. So that's actually being oxidized. And that's okay. You can have oxidation and reduction occurring in the same species. So when the O's in the peroxide become elemental oxygen, they're just supplying the electrons for them to be reduced into water. Okay, so that would be another example of a redox reaction. Kind of a different one. All right, let's do a single replacement. This is your pennies from last year that you did, a single replacement. So we have zinc here, Zn, and hydrogen chloride, hydrochloric acid, HCl. And then we have zinc chloride, ZnCl2, and hydrogen H2. And so if we do oxidation numbers here, we're going to have the Zn uncombined is 0. HCl is going to be +1 and -1. This is the rule where we can use hydrogen. We can also use that chlorine is more electronegative, so it would have its charge as an ion, or that it's overall neutral. Same thing over here. Chlorine is more electronegative, so it would have the same as its charge as an ion, which means zinc would have to be a +2 in this case. And then we have elemental hydrogen, which is 0. So what you guys can see is that zinc, as it goes from the element to being in that compound, is oxidized. And it is the H in the hydrochloric acid that goes from +1 to 0, which is being reduced. Okay, so another example of an oxidation-reduction reaction. You can see how important keeping track of those oxidation numbers are for this process. Okay, well, tell you what, that's all I have for you. Next, we're going to get into balancing redox reactions. We'll make sure you're all set with 5.1 before we dive into that on Wednesday. So have a wonderful day, and I will talk to you soon.